So my name is Helge Holden, and it gives me great pleasure to introduce the next speaker, who's Professor Michael Jordan. Michael Jordan is professor at the Department of Electrical Engineering and Computer Science at the University of California in Berkeley, where he came in 1998. Before that, he was a professor at MIT for 10 years. He holds a PhD in cognitive science from UC San Diego from 1985. Professor Jordan has received numerous honors, for instance, the David E. Rumelhart Prize, that is awarded annually to individuals for significant contributions to the theoretical foundation of human cognition. He's a member of US Academy of Science, National Academy of Engineering, American Academy of Arts and Sciences. Professor Jordan, the floor is yours.
Thank you. Pleasure to be here. So my talk today is going to be about optimization and computation and statistics. In fact, most of the words I'm going to talk about were already alluded to in the previous talk. I even heard symplectic at the end, and there was a lot of dynamics and computation. So in fact, there's going to be relationships between quantum and statistics going forward, which I think are going to be fascinating to see. I need some help. I had my slides up there, now you've lost them. There we go. Now I've skipped way ahead, all right. Okay. So the topic's going to be optimization. It was a topic that was, when I was a graduate student, was viewed as dead, 70s and 80s. Dead in the sense all the hard problems had been solved and people were moving on to other things. And there could be nothing that's less true now. It's very lively and very central to many of the fields concerned with computation and statistics. So the broader scope of what I'm going to be talking about is relationships between inference and computation. It's really, in our era, I think if Gauss were alive and Kolmogorov, this would be what they were working on. In fact, Kolmogorov already was. Statistics is developed 300 years ago or more. It has to do with inference about the real world, not just what's inside of a computational machine. But it's algorithmic field as well. There are procedures in statistics. However, it was developed before there was computer science. So there weren't computers to try ideas on, and there wasn't a formal theory of computation. That's all changing because most data analysis problems nowadays have a time budget. If you're doing data analysis for a transportation system or a medical system or a finance system, there's timescales that are relevant: seconds, milliseconds, microseconds, and so on. The classical statistical theory has no role for time. And it has equations that are trade-offs among data complexity, risk, dimension, and so on. But in those equations, you will not find runtime. And on the other side, in computer science, you will find trade-offs involving runtime and memory and energy and so on, complexity measures. But you won't find statistical risk generally. So putting those two ways of thinking together is the grand challenge of our era. So I'm going to suggest that optimization has played the role of trying to bring these two fields together. It's provided algorithms and moreover insight. Specifically, if we start looking at lower bounds, the insight is coming via optimization. On the other hand, going the other direction, modern statistics has to do with billions of data points and millions of variables. And that's not the kind of regime that classical optimization found itself in. So there's new mathematical issues, new computational issues that this brings to the fore. And moreover, the computing platforms have changed. They're now parallel distributed. There's GPUs and TPUs and so on. And that has a major effect on the kind of algorithms that are useful in practice. So there probably are no journalists left, certainly by this part of the conference. But just let me say this general problem of bringing computation and statistics and data at large scale together to solve real-world problems has many other buzzwords associated with it. Machine learning, deep learning, AI. You've probably heard these during other earlier talks. I think of them as just other words for the same general enterprise, and I don't particularly like any of those words. I think their scope is limited. The appropriate scope is the general problem of algorithmic decision-making under uncertainty. And then we add then in large-scale networks and markets to focus it on bigger problems, not just about an individual intelligent system. So if you start thinking about that level of generality, it's sort of all of mathematics and engineering, if you will, but it's emerging topics in these areas. These are the things I think that Kolmogorov had in mind, and von Neumann and Wiener and so on. Wiener called it cybernetics, Blackwell and Wald. And those people would have not been able to give you an answer if they said, are you a statistician or a computer scientist? They were both, right? They were also control theorists and economists and so on. I think students these days don't think of themselves as belonging broadly to those disciplines. So I think that needs to be changing. And of course, mathematics provides the backbone and the communication fiber for all of this change. Okay, so let me return to this issue, computational statistics being brought together via optimization. So what kind of ingredients are we going to start putting together? How are we going to start to build up theory and practice? So at this very, very large scale, that is the reality in real life, in companies and in science, the following ingredients have turned out to be really critical for success stories. One is to focus on gradient-based optimization. The generation I learned optimization about, it was all focused on Hessians and Newton's method and so on, and higher order versions of that. That's pretty much gone. I've not, in 20, 30 years, seen successful applications of that at large-scale problems. It's hard to calculate Hessians, and it's hard to estimate them robustly. Now, we always have stochastics in these problems. We don't observe things exactly. It's just the field of statistics. There's likelihoods, and there is errors of all kinds, including bias sampling and so on and so forth. So we have to both exploit that and face it. And then finally, this notion of acceleration, which came out of the Russian school of optimization, talking about algorithms that are optimization algorithms, but they are the fastest possible optimization algorithms. So in some sense, they are the optimal optimization algorithms. And giving mathematical content to that, it was a real achievement in the Russian school. And to this day, if you're really trying to get at foundations of optimization, you start to think about acceleration. And so my talk will focus on acceleration and then relate it to some of these other ingredients, in particular stochastics. So here's the outline. We're going to talk about saddle points, and we're going to talk about escaping saddle points. If you're in non-convex optimization, that is one of your core challenges, is how to escape saddle points and do it efficiently, not just in convergence rate, but in dimension, because we are very much interested in hundreds of thousands of dimensions. Then we're going to talk about acceleration, and we're going to bring some physics to bear and some geometry. Acceleration is a phenomenon which I view as best approached in continuous time. It's not been approached in continuous time. Most optimization theory is done in discrete time, and most computer science theory is done in discrete time. If you're thinking about acceleration, you're trying to move faster, you really need to embed the problem in a continuum. And so that's going to be an important part of my talk. And then I will talk about implications of that for various other areas involving stochastics. So let me start with this issue of avoiding saddle points efficiently. I mentioned some colleagues that we've worked on this for the last 2 or 3 years. It's recent work. So we're going to be talking about non-convex optimization in a fair chunk of this talk, not always. It's not been the focus of much of the work in optimization, beautiful work on convex optimization, but the real world has many, many interesting non-convex problems. It used to be, at least in my era in the 80s, that bad local minima were thought of as really the critical problem, the challenge. There might be exponential numbers of them. It might be that the algorithms would just find bad ones and so on. And just both empirically and partially theoretically, that's been mitigated over the years. They remain to be a problem, but they seem to be less of a problem than one would have thought. All right? But if you're going to have lots of local minima, topologically, you're probably going to have lots of saddle points as well. In fact, provably, you have many, many more saddle points than you have local minima. And often the practical problem is the saddle point. So you're trying to optimize on a high-dimensional surface, and you have huge numbers, in fact, kind of rings of saddle points. What you will see as you're descending the surface is the function value will start to go down very quickly. It'll flatten out. And it may flatten out for a very, very long time, and you think you're finished. And you run some diagnostic test, and it looks like you're finished. But then if you wait a little longer, it goes down again, and then it flattens out again. And what's happened is you're hitting these rings of saddle points as you're moving towards perhaps a global optimum. So it's critical to understand how fast you move past those saddle points. Is it way too long that no one would wait that long? And how does it vary as a function of dimensionality? Okay, so here's a picture of a saddle point. If you don't know what one is, of course, in this audience, I don't think that's an issue. But this is a two-dimensional one, and we're going to think about hundreds of thousands of dimensions. So there's going to be perhaps only very few directions where you can escape. And mostly you go back uphill, and it's a problem. It'll take you a long time to find those directions, perhaps. So we have to think about that algorithmically. So efficient in this case is going to be a computer science word, and we're going to specifically not just get rates, we're not going to hide the dimension dependence. We're going to try to get the dimension dependence, and in fact even get many of the constants in the problem as well. Okay, so a little bit of background for the particular result I'm going to tell you about. As you may know if you've studied gradient flow, there are asymptotic results saying that gradient flow will avoid saddle points. That's stable manifold theorem. That kind of result hasn't been studied in the discrete literature for gradient descent, and we did that a couple of years ago. So asymptotically, gradient descent will avoid saddle points rather generically. But that's an asymptotic result, and that's just not of much interest to us in the practical world of our field, so we go for non-asymptotic results. And there we already have a negative result, which is the gradient descent can take exponential time in the dimension of the space to escape saddle points. And this is by construction of some bad functions, and they're not such exotic functions. They're one you would actually run into in practice. All right? But in the meantime, we already knew of a result that said that particular stochastic gradient descent, a particular form of stochasticity, allows you to escape saddle points in polynomial time. Okay, so that is a non-asymptotic result, but it just says polynomial. So if you're a computer scientist, that's really fascinating. Polynomial exponential barriers, of course, core area of focus. But if it's d to the 50th power, or even d to the 3rd power, it's not of much interest to us, because d for us is hundreds of thousands. So it really, if these algorithms are really working in practice, it must be that it's not a high-order polynomial. But what is it really? Okay, so let's set up a problem here. F will be smooth for most of our work. It will sometimes be convex, but often non-convex. But let's just consider an algorithm, first of all, gradient descent. Just take the gradient assumed to exist, or perhaps subgradient, at a point, and take a step size, eta, and move in the direction of the gradient. So this was certainly known to Newton, but in the 1800s was studied quite a bit. So many theorems about it. It converges kind of clearly to the global minimum. But more interestingly, the number of steps that you take to arrive within an epsilon ball of the global minimum is independent of the dimension of the space. So that's less well appreciated, but it's really, really amazing and important. So you can run gradient descent in infinite dimensions, and it will take just as many iterations as if you're in a finite dimensional space. So that's in some sense the best we could hope for some algorithm. We can't expect that in the non-convex case, but what could we possibly get in the non-convex case? So non-convex case, we're going to have local maxima, we're going to have local minima, and we're going to have probably lots of saddle points. All right, so first of all, how do we make sure we don't hit those saddle points? How do we characterize saddle points? And then how do we get a convergence rate? So first of all, let me note that this is not just a mathematician's exercise. There are very, very many non-convex problems that are of great importance in the modern data analysis world that are non-convex, but they provably have only a single global optimum. Okay, so what's the difficulty of them? Well, lots of saddle points. In fact, exponential numbers of saddle points. So if you think about PCA, principal component analysis, or CCA, the first and smallest eigenvalue, that's a convex problem, but all the others is non-convex. Orthogonal tensor decomposition, dictionary learning, phase retrieval. These are practical problems used in biology, physics, and so on and so forth. They are non-convex, but they have provably only a single global optimum. So if you're going to study these things mathematically, really the first thing to study is saddle points and how fast you can avoid saddle points. Okay, so let's start to set up a little bit of structure. The classical theory for the convex case is to study first-order stationary points, FOSP. So we assume the minimal assumption is that it is smooth, meaning the gradient has a Lipschitz, the gradient is Lipschitz. And instead of asking the gradient be exactly 0, we put an epsilon ball around the stationary point and solve this for all epsilon, so we get a convergence rate, okay, as we approach as the ball gets smaller. Okay, so here's an example of a theorem. This is Nesterov, 1998. The gradient descent converges to a first-order stationary point, and it does so in a number of iterations, which is 1 over epsilon squared. All right, so if I want epsilon to be really small, the number of iterations is going to go up accordingly. Okay? So is this fast or slow? It's relatively fast, but it's what it is. It's what gradient descent is. And moreover, there are no hidden constants here. There is the initial distance to the optimum, f star. That has to be in any result. If you start far away, it just takes you time to get there. And then there's the Lipschitz constant, and no other free constants. So critically, the number, there's no d here. The number of dimensions does not appear in this equation. Okay, so now let's move on to the non-convex case. So we'll add another assumption. The minimal assumption here is that we need to say something about the second order structure. So let's say the Hessian exists and that it is Lipschitz. So we have now a new constant rho. And we're going to now define another kind of stationarity to go a little bit beyond where we were before. So we can distinguish between saddle points and minima that we're interested in. So again, we want the gradient to almost vanish. And we want the minimum eigenvalue of the Hessian to be greater than or equal to 0. That would make us have a bowl shape, but then we'll give ourselves a little bit of wiggle room to, again, get a rate. And that's parameterized in a maybe odd way by the square root of rho epsilon with a negative sign. So we're not introducing any other parameters. We just take the epsilon, which gives us our rate, and then rho is the Lipschitz constant for the Hessian. So this is a standard parameterization of this class of stationary points. Okay, so we're going to analyze the following extremely simple algorithm. It's kind of the minimal algorithm to see if we can get an actual rate and see if the rate is meaningful. Is it polynomial, is it exponential, or whatever? So it is going to be gradient descent. So that's line 4. But it's also going to be stochastic, because we know we need stochasticity to get away from exponentiality. And so this is a very, very simple form of stochasticity. We're simply going to add noise in a ball around the current iterate. The radius of the ball, I will be able to tell you what that is. That's r. And we're going to do this, we're going to add perturbation sporadically. So if the gradient is less than epsilon, we will add perturbation in that moment, if we've not added a perturbation within the last capital T steps. All right, so we will wait, and we will add perturbation again. So think of this as a sufficient condition for the kind of results I'm about ready to show you, not necessary. In fact, we have other styles of algorithm where we're able to get the results. We've done that subsequently. This was our first result. Okay, so let me show you our theorem. The theorem is that this form of perturbed gradient descent also has a convergence rate to second order stationary points. So now we're in the non-convex case. And it does so in a number of iterations, which again goes as 1 over epsilon squared. And again, it has the Lipschitz constant and the initial distance in the numerator. So this really is amazing. It's the best you could expect. It looks exactly like gradient descent. But now I'm hiding the dimension dependence. That's the little tilde. And then I'm being honest about it. So the dimension dependence turns out to be polylogarithmic. So it's logarithm of dimension to the 4th power. All right? So it's not polynomial. It's much, much better. It's logarithmic. Right? And so I think this is one of the first results, maybe the first, that gives some substance to the idea that stochastic gradient descent works in very, very high dimensional spaces, because its dimension dependence, it can't be constant, but it is actually only logarithmic, polylogarithmic. So I believe that logarithm. I believe that's true. But I don't believe the 4. I believe that's an artifact of the proof technique, which I'm about ready to tell you about. So just putting this side to side with Nesterov, it really looks the same. The only difference is this tilde, where we've got the dimension dependence not being constant or independent, but being polylogarithmic. Okay, so let me tell you a little bit about the proof technique that we have used, developed here. So this is really some differential geometry in some sense. So around these saddle points, there's some geometry. In particular, there's going to be what we're calling a stuck region, a region that if you are in, the flow of the dynamics, the exponential flow gotten by the negative eigenvalue, is not enough to pull you out of the stuck region for a very long time. So you don't want to be in this stuck region. And whatever stochasticity you have, it needs to be calibrated so you will jump out of this region. Okay? And we need to know the width of that region as a function of dimensionality. So the early work on this that established these polynomial rates replaced that pancake-like shape with a flat slab, okay, in high dimensions. All right? It's not a flat slab. Because the Hessian is varying, it varies a little bit. It's really a pancake. All right? Replacing it with a flat slab gave a bad upper bound. It gave this polynomial dependence, which is not true. All right? So how do you get that it's the actual width of this thing? Well, if you're really good at differential geometry, you could probably attack this with your tools, whatever they are. So I'm in Brazil, long tradition differential geometry. Perhaps someone can attack this problem. We did it instead with probability theory. And so the technique we used was a coupling technique. And what you do is that you start 2 stochastic processes, 2 diffusions, a distance r apart, and you vary r. For small values of r, these diffusions will couple very quickly because they're not getting the dynamics of the exponential The power method is not bringing them apart. But as you start to grow R, eventually there will be a phase transition, and the diffusions will not couple. They will flow apart. And so when you calculate that phase transition, you're getting the value of R, and that's the width of that stuck region. Okay? So it's just probability theory used in a fairly straightforward way, effectively substituting for some differential geometry. I think that's what gives you the logarithm to the fourth, and probably some deeper geometry would probably remove the 4, but that's our technique. There's going to be a lot more coupling arguments later in this talk. It's been one of our main tools. Okay, with that in hand, we're now able to start to study a whole bunch of other problems that have been viewed as open for the last several years in the optimization literature. First of all, we're going to talk a little bit about acceleration, Nesterov acceleration. It's this notion of methods that somehow go faster than gradient descent, even though they're only using gradients, and in some sense are the best possible algorithms. They arrive at an oracle lower bound. And it's been an open problem that's been studied mostly in the convex setting. It's been an open problem whether, in the non-convex setting, acceleration helps you. So in particular, we can now formulate that crisply as, does acceleration move you past saddle points quickly? So acceleration is a notion of kind of momentum, and intuitively, if you're arriving near a saddle point, you might think the acceleration helps you kind of blow past the saddle point, but it's just been an intuition and it's not been established, and we'll establish this in this talk. What other stochastic models can we use instead of round balls? Are there other kinds of stochasticity? And then how do acceleration and stochastics interact? In particular, can we accelerate diffusions? Can we accelerate stochastic differential equations? That's been an open problem. Okay, now, so to answer these questions, we have to study this notion of acceleration, which hopefully many of you have heard of, really important development in optimization theory, and we need a deeper understanding of it than it's been available to date. So here's where I'm going to go into continuous time, very strangely perhaps for a person working in optimization, but I think critically. And let me just recognize colleagues here, Andre Wibasoni, Aisha Wilson, been students with me at Berkeley, and Mike Betancourt at Columbia has helped us out as well. So a lot of topics that are familiar and probably warm your heart, variational, Hamiltonian, and symplectic. And I'm going to argue they're really critical to understand this phenomenon in optimization. They haven't been, to my awareness, used in optimization, but I think they're really the appropriate tools. So let me be a little bit grandiose. The fields that I'm aware of that are sort of the most mature mathematically are making very deep use of the fundamental theorem of calculus. There's a lot of derivatives and there's a lot of integrals, and you go back and forth between the two and include some optimization. So certainly physics is the poster child of this. Newton wrote down F equals ma, expressed the laws of nature in terms of derivatives. And Lagrange came around 100 years later and said, I'm going to rewrite those laws using integrals instead. I'm going to integrate and I'm going to get volumes. And I'm going to then optimize over those volumes. So he both introduced integrals and optimization, and he showed you could get the same physics. And then those two perspectives, if you're a physicist, are part of your daily bread and butter. You go back and forth between the two all the time. Probability theory, if you follow the work of Talleyrand, is full of these paths, these smart paths. And that's exactly using fundamental theorem of calculus and using derivatives and integrals in a very deep way. And statistics has borrowed these tools. Laplace expansion, saddle point packs are widely used in statistics that both have derivatives and integrals. And then the numerical disciplines. Finite elements is taking a PDE and expressed in terms of derivatives and replacing with patches of integrals variationally. So what about optimization? Is it deep in this same sense? Is it kind of exploited these two perspectives? And I'm going to argue that no. You can pick up as many papers as you want in an optimization journal. You'll see lots and lots of derivatives. Gradients, Hessians, bordered Hessians, you name it, but you'll almost never see an integral sign. You'll see it in a Taylor expansion where someone's trying to ignore something. So I think that there's still immaturity in the field, maybe surprisingly after all these years. So let's try to motivate this now. Let's go back now to convex optimization, where we've had this classical study of acceleration phenomena. Let me tell you what the acceleration phenomena is. Here's gradient descent again written down, slightly different notation. And let's add a fact that in the world of convex optimization, I can prove that after 1 over k steps, you'll be within a epsilon ball of the origin. So there's a convergence rate over the class of smooth convex functions. The convergence rate is 1 over k. Okay? So that's a relatively new result. It's over a class of functions. It's not for a specific function. So at some point, someone asked, and that someone was Arkady Nemirovsky, is this the best you can do? So he's now at that point asking a complexity theoretic question. So he could go to complexity theory, perhaps, and look at the Venn diagrams you see and ask, where do I place, where am I in that Venn diagram? That turns out not to be a particularly helpful way to go. So he invented his own complexity theory. He said these classes like Turing complexity and beyond are too powerful. They can do too many things. I can't get a meaningful lower bound. So he said, what I'm going to do is invent a new computer which allows me to look at function values and gradients of functions, and its algorithm is that it can take steps within the linear span of all previous gradients. So there's his little computational model, if you will. It's not Turing complete, but it's interesting. It can do gradient descent, it can do conjugate gradient, it can do lots of things. It's a powerful computer. And moreover, in that computer, he was able to prove that there's a lower bound, that if you're doing convex optimization, that the lower bound is a rate which is 1 over k squared. Okay? So it was a productive model because he was able to get an interesting rate which is close to the upper bound. That doesn't often happen in computer science. A lot of the lower bounds are far from the upper bounds. All right, for a while then, one could wonder, is that gap real? Gradient descent, if you're only allowed to look at gradients, seems optimal. It's steepest descent. But there's this gap. Maybe there was a better argument that gave you 1 over k as the lower bound. Well, it turned out not to be true. So in 1983, Yuri Nesterov, again in the Russian school, or the Soviet Union at that time, published the following algorithm. It's got 2 pieces to it. How many of you know what Nesterov acceleration is, by the way, just to get a show of hands? Yeah, it's amazing. In this community, it's like 10, and it's probably one of the top 4 developments in optimization in the last 40 years. So anyway, Yuri Nesterov, an important name, developed this algorithm. It's got 2 pieces to it. The first, there's now a y variable and an x variable, 2 variables. The y variable does gradient descent in the x, and then x takes a linear combination of the last 2 y values. So it looks like it has some momentum or a heavy ball or various interpretations of this. But the key is that you can now analyze this with a tool that Nesterov developed, and you can show that its convergence rate is in fact 1 over k squared. So it beats gradient descent even though it's only using gradients. That's pretty amazing. Also, it's not a descent algorithm. It will go downhill and then it'll go back uphill again, which seems very surprising if you're trying to get down as fast as possible. Okay, so in the intervening years, there's been huge developments. This has been very productive. People have taken many gradient-based algorithms or other kinds of algorithms and accelerated them, adding this style of 2 steps instead of just 1 or maybe 3, and taking many algorithms. The resulting algorithms are called accelerated methods, and they are often faster, and they often achieve Oracle lower bounds if those are available. But there's still a lot of mystery here, and there's been many proposed explanations involving connections to other areas of mathematics, and lots of beautiful work that's been done, mostly very recently. I think that they've not quite got there yet. There's something missing. They're very limited, often in scope, but also they don't really explain the phenomenon in, to me, a mathematically satisfactory way in generality. And what I think is missing here is that, in fact, it's all being done in discrete time. So what we're doing is, in some space, we're hopping through a discrete set of points under gradient descent or some other algorithm. And I'm asking to hop among those points more quickly. Right? What does that mean, to hop through some points more quickly? You need a continuum. You need to embed the problem in some kind of a continuum where going more quickly has a mathematical meaning. All right? So that's critically what I think has been missing and what we're going to now try to add. Okay, so let's do that for gradient descent. If someone had told you about gradient descent, you might try to embed it in a continuum, and you would now have rediscovered gradient flow, of which there's been hundreds of years of work, and Ambrosio in this conference is a leader in that and talked about it. Still studied to this day in mathematics. There's no step size, that's just a differential equation. I'm going through past the gradient. I have a vector field. And this has a convergence rate. So if the function f is convex, I can prove that I'll be within epsilon ball of the optimal within 1 over t steps. So just like 1 over k in discrete, it's 1 over t in continuous. All right, so now you can go back to those 2 equations of Nesterov, and you can ask, what if I take the step size to 0? I'm going to get some differential equation. What differential equation do I get out? So this was done in a nice paper by Sue, Boyd, and Candace, Stanford, in 2014. They did that, and there's the differential equation that pops out. X double dot, it has a mysterious 3. It's non-homogeneous, and it has the gradient. So you can't solve this, but you can use Bessel functions to start to understand it. You can start to get an idea of why, the fact that it oscillates. goes up and down, and so on. So we looked at this equation, and this triggered, I think, the following thought. If Lagrange had looked at that equation, he would have probably said, where does that come from? Is there an underlying energy? Is there a principle that delivers that differential equation? Why that differential equation? Why is that special? And can I get similar differential equations for other problems, other geometries, other assumptions, other oracles, and so on? Can I get a generative principle for these differential equations? And then having gotten that, some kind of energy, does it have mathematical properties that allow me to understand the phenomenon in some generality? Okay, so that's what we've gone after in the last several years, and I think we have at least partially achieved those goals. So here's the Lagrangian that we're going to talk about. So I've written it here, no mysteries, this is it. We call it the Bregman Lagrangian for reasons that will become obvious. It is a time-varying Lagrangian. Is littered with these functions alpha, beta, and gamma. These are just arbitrary diffeomorphisms. They give me a space of algorithms, not just a single algorithm. So they are in the hands of the user to pick alpha, beta, and gamma. And I'll give you some examples later. So that's not the important part. The important part is the first term, which is a Bregman divergence. If you haven't seen a Bregman divergence, I have a picture up there. I'm trying to measure the distance between x and y in a metric space, and I put an auxiliary function h above the space. And then I take the linear discrepancy at y from the linear approximation at x. That vertical direction in red measures the distance between x and y on the x-axis. Okay? If h is quadratic, this is just a fancy way of writing the Euclidean distance between x and y. It's just a variational way of writing that. But h can be logarithmic, in which I get Kullback-Leibler divergence. It can be all kinds of other functions and widely studied in convex analysis. All right, so we're using Bregman divergence in continuous time. So our Lagrangian there is in continuous time, x dot, and t. And the Bregman divergence is the first term there, depends on the choice of h, that's another degree of freedom. And it measures the divergence between x, where you are now, and x plus a time-scale velocity. So kind of the motion is in some direction, the flow is in some direction, and we measure sort of a energy, if you will, along the direction of motion. And then we subtract off a time-scale version of the function you're trying to go downhill on. So if you think of f as a potential we're trying to go downhill on, the first term is like a energy, a kinetic energy. And in fact, if you set h, I think I have a slide on this, yes, if you set h to quadratic, then that just simply reduces to 1/2 x dot squared. So it literally is the kinetic energy. So I have kinetic minus potential, this literally is a Lagrangian. Okay? But in more generality, it's a Bregman Lagrangian. So what do you do with Lagrangians? Well, you do what Lagrange told us to do. By the way, I do like to mention in audiences like this that Lagrange, despite the French-sounding name, was an Italian. I'm also an Italian citizen, so I have a little pride in that. His name was Giuseppe Lagrangia, a little-known fact. So Lagrange said, what we're going to do is get differential equations by a variational principle. We put the Lagrangian inside of an integral. Then we minimize over paths that integral. Okay? And as you all know, a necessary and sometimes sufficient condition for optimality is the Euler-Lagrange equation. So I just hit that Lagrangian up there with some partial derivatives and a time derivative, and out it's going to pop a differential equation. So let's do that, and once and for all. There's a master differential equation for this Bregman Lagrangian. So there it sits at the bottom of the page. So I have x double dot. I have some non-homogeneous term, and then I have a bunch of geometry, really, depending on this choice of function h. Okay? So I argue this is the equation that captures acceleration in some generality. If you set alpha to logarithm t, and if you set h to quadratic, this reduces to the Suboid and Candes equation, which has a convergence rate of 1/t², by the way. But this can give you mirror descent, it can give you accelerated cubic regularized Newton, and so on. They're all sitting inside of this differential equation. Okay? So there may be things outside the scope, but I don't know of them at this currently. So that's great, but what more mathematically can you learn from this framework? Well, you can get a convergence rate once and for all for this entire family. Normally, convergence rates are 2 or 3 pages of convex analysis, Cauchy-Schwarz and so on, nothing particularly hard, but 2 or 3 pages. We're going to get in one line a convergence rate for the entire family. And here is that convergence rate. It is e to the minus beta t. Now, beta t is a degree of freedom you have as the algorithm designer. So it's kind of maybe odd that suggests I can get whatever convergence rate I want. And that's going to actually be true in continuous time. So we're going to dig into that in a minute. Anyway, the proof is simply to write down a Lyapunov function involving the Bregman divergence. So there it is, E of t, and we take the first time derivative and ask that that be less than or equal to 0. And that holds if and only if I have that convergence rate at the top. So there's a one-line proof of convergence rate. Okay, so now we look like we're getting exponential convergence rates, which we know is not possible, right? We get these polynomial rates, 1 over t, 1 over t squared, maybe 1 over t cubed, and so on. How is this possible? It is possible in continuous time, all right? So here's where it starts to get a little bit interesting. So let's suppose that I know that, suppose that I choose beta of t to be logarithm of t, okay? If I plug that in there, then my convergence rate will be 1 over t, all right? But now I'm going to take that choice of beta, I'm going to put it back in the Euler-Lagrange equation, and it will deliver a particular differential equation that I could discretize. That differential equation will be gradient flow, and when I discretize it, I get gradient ascent. So it's a long, crazy way to go get back gradient flow, which has a known convergence rate of 1 over t, and discretize it stably. And let's suppose that Rafi comes along and says, I'm going to go faster. I'm going to go at rate 1 over t squared. So he sets his beta of t to be 2 log t, okay? When he sets beta t to that, he goes back to the Euler-Lagrange equation, and it will pop out a differential equation. That will be the Nesterov continuous time differential equation, which he also can discretize, and he can get an algorithm. Someone else here can pick t cubed, and they can actually achieve that. The Euler-Lagrange equation will generate a new class of algorithms that have convergence rate of 1 over t cubed. Now, what's interesting, if we go back to this picture here, all of those algorithms will follow the same path in phase space, all right? So that's what's interesting. The acceleration phenomenon is not the rate, it's the path. And why is that happening? Because this Bregman-Lagrangian is covariant as a mathematical operator. Okay? It's an easy argument. So we're going to follow, all these people will follow the same path. And our young Greek friend here, Daskalakis in the front, say, well, I'm going to go faster than any of you old guys. I'm going to set beta of t to be t, and I'm going to go at rate e to the minus t. And if he does that, he will get out a differential equation, which in continuous time follows the same path that all of us do, but just goes faster, super fast, all right? But in some sense, that's not interesting. It's just that we're using different clocks. And so it's like Einstein said, the clock doesn't really matter, okay? It's the path that matters. Okay, so that's the first step that's interesting. That's in continuous time. We've discovered a little bit of structure here. But now we need to discretize to get this as an algorithm on the computer. And we know we can't go arbitrarily fast, so something must be breaking at some point. These people going into polynomial rates, 1 over t, 1 over t squared, can discretize and get an algorithm. But our young Greek friend here is going to try to discretize, and something must break. Okay? And what is a fact, a mathematical fact, is that he cannot discretize his differential equation at that rate. It's not possible to stably discretize that differential equation. Right? Now, we would have only discovered that fact if we were working in continuous time. In discrete time, it's a mystery. That suddenly, at some rate, I can't achieve it. But in continuous time, it's not a mystery. Okay, so these were some mysteries that we've been working on for about a year now. Why can't we discretize when we're using these ambitious clocks? What happens when we arrive at a clock speed where we can discretize? How do we discretize once it's possible? Okay, so the mathematical structure that I've been using in my group to try to understand these mysteries is symplectic geometry. I learned about it when I was a young professor back at MIT, and it's stuck in my brain ever since, and I finally found a way to use it. I should say I think that it's a sufficient way to solve these problems. I don't think it's necessary. And I think it actually has a few disadvantages, which I'm going to allude to here in a minute. But nonetheless, it's allowed us to make real progress. So in this audience, I hope this slide was actually not prepared for you. It was prepared for a different audience that doesn't know about symplectic integration, but I hope that all of you know. The tradition goes back to Hamilton, Poincaré, Jacobi, and others. And so they had some equations of motion from physics, F equals ma, Maxwell, fluid flow, and so on. And for some reason, they were interested in discretizing those differential equations, and they wanted to discretize them in a way that still reflected the physical properties, physical invariance. So those equations had certain laws, conservation of momentum, energy, volumes, and phase space. And they wanted to discretize those differential equations in a way that you exactly conserve those physical quantities. Now, someone in the audience maybe can come up later and tell me why they were trying to do that. Computers didn't yet exist. They were just prescient, smart people, I think. But they thought that was an interesting, important mathematical challenge. All right, and the perspective they came up with is, just to explain it briefly to an audience that may not need it, is instead of thinking about a vector field as a vector leaving a point, a vector flow, you think about a triple of vectors at every point. And as that triple moves along the flow of the differential equation, that triple will shear in some way, and you would like to ask that volume element stay constant as it shears. Okay? And in general, there's an exterior form on a manifold which you want to stay constant. A volume element is a determinant, so you're just putting a constraint that a certain determinant stay constant as you move in a certain way. So that's a mathematical constraint, and you can ask for algorithms that respect that, and they achieve that. And so their integrators were not just Euler integration of an explicit or implicit form. More or less, they're an interlaced collection of explicit and implicit. There is a wonderful book, which one of the authors was here and gave a plenary as well, on geometric numerical integration, which lays this theory out and brings it up to the modern day. It's an absolutely beautiful field. So how's that related to what I've been talking about? Well, if you do the numerical analysis of these procedures, forget the physics, the motivation. In the numerical analysis, because you're reflecting the symmetries in the underlying Hamiltonian to conserve these things, various error terms cancel away. All right? Those error terms mean you can take larger step sizes and stay stable. In fact, in some sense, largest step sizes up to some order. And that ability to take large step size and move quickly is a connection to acceleration. Right? So that was the thought that I had. So now we just take that book or others and just execute the program there in our domain. So we have this Bregman-Lagrangian. It's time varying. First step is to turn that into a Bregman-Hamiltonian just with a Legendre transform. That's straightforward, convex duality. The next step is to take that Hamiltonian and make it homogeneous by adding an explicit conjugate pair, time and energy. And now we have a classical Hamiltonian, or not so classical, but we have a Hamiltonian, and we can apply a symplectic integrator to it. We have now done that, and so now we have a chain of mathematics that starts from the problem specification and goes all the way to an integrator of a differential equation that gives you an algorithm, and there was no creativity needed. There was no Nesterov or no smart new person creating some algorithm. It was just this mathematical framework. And it works beautifully. So this is on a high dimensional F. This is symplectic integration of this Bregman-Hamiltonian. And it is going down at the oracle rate for this particular problem. And you can see it's going up and down, oscillating, but in a very nicely controlled way. If you compare this to Nesterov, and I have now a slide comparing to Nesterov on a different function, you see this thing is actually, the oracle rate is a worst case rate. So it's coming down at the oracle rate, and then both algorithms actually go a little faster near the end. So it looks like it's sort of as good as Nesterov. And this is a bit of a discovery, because Nesterov has been kind of the state of the art for quite some time. But it's actually better than Nesterov, because it's a stable symplectic algorithm. If I now turn up the step size, Nesterov goes unstable, whereas the symplectic integrator stays stable. So the whole thing is shifted over by a factor of about 5. This is about 5 times faster than Nesterov on this problem. Okay, so for want of time, I'm going to move on a little bit, but I hope I intrigued you a little bit by this connection to simplicity and optimization. The problem we're trying to ask is there an optimal way to optimize? And we're arguing that can be characterized in a Hamiltonian or Lagrangian framework in continuous time, and we get a lot of insight there. All right, but then we need to move back to discrete time to get algorithms, and in that step, symplectic ideas are very, very useful, and they may, again, not be necessary. Now, there's one little gotcha here, which is that, the Hamiltonian framework is sort of set up for things like the cosmos, where you oscillate, right? You don't bleed away energy, it's homogeneous. In optimization, we're definitely not wanting to oscillate. We're wanting to go in and stop. If you're using these ideas for a Markov chain Monte Carlo, an algorithm which is not supposed to stop, they kind of feel a little more appropriate. And in fact, leapfrog algorithm is used very successfully inside of Markov chain Monte Carlo. But we're trying to do optimization. And so in fact, this behavior at the end of kind of going down quickly, we got that in actually by adding a gradient flow term to our symplectic integrator. So we cheated, in essence. We didn't just use the Hamiltonian. That alone gives you that rate, that oracle rate, just continuing all the way to the optimum. Okay, so in that sense, this perspective, I think, needs to be augmented in a way that makes it more appropriate for optimization, if you want to stick with optimization. Okay, take a pause for a second here. So let's now, with those two ideas in hand, we've studied a little bit of the story of non-convex optimization, in particular saddle points. And we've developed a theory of acceleration that allows us to think about dynamical systems for optimization in perhaps a broader way. And so now if we see we can bring those kind of ideas together and get new insights for non-convex optimization and acceleration. Okay, remember my setup. There's nothing new on this slide. So I just have some smoothness assumptions on Hessian and gradient. And remember our definition of a second-order stationary point. So we're back to where we are. So we're now in this non-convex setting. We've got a saddle point, and we have this perspective of these algorithms, acceleration that kind of go up and down, and how does that interact with the geometry of saddle points? Okay, so accelerated gradient descent, that's what AGD stands for, is not a descent algorithm, as I've alluded to. We have shown in the previous section that we want to lift the problem into a phase space, not just stay in the position space and make use of a Hamiltonian. Now, when we do that, it turns out that AGD almost becomes a descent algorithm, in the Hamiltonian, not in the original function value. And if it were just a descent algorithm, then in that case, we'd be really done. We'd have the best Hamiltonian for the problem. It turns out not to quite be, but it's almost. And we can identify and diagnose the little bit of remaining non-convexity, and we can add an algorithmic component which handles that. It's called negative curvature exploitation. It may be eventually possible to move beyond that, but that's kind of where we and others are in the literature at this point. The Hamiltonian we use here is extremely simple. So remember, AGD is a second-order differential equation, x double dot. All we're going to do is kind of integrate, look at a first integral. So we integrate, multiply by x dot, and integrate from t1 to t2, and we get that equation with the blue and the red terms. And you can see that f plus 1/2 of the kinetic energy appears on the left and right, and then there's a negative term. Okay, so that suggests that we have a function which is actually descent algorithm. At each step, it's going downhill because there's just they're related by this negative term. Okay, so I don't want to go through this slide, but there's no new ideas being introduced here. This is the algorithm we're going to analyze. This is what we're going to now call perturbed accelerated gradient descent. So it puts the two ideas together. It is going to be Nesterov acceleration on bullets 4 and 5, and then it's going to add a perturbation on line number 3. And it's going to do that sporadically, as you can see on line number 2. So it puts these two ideas together. And now the question is, can you analyze this and get out a convergence rate? And is that convergence rate still 1 over epsilon squared, meaning that acceleration doesn't help you get past saddle points, or is it faster? Okay, now I don't want to go through this slide. This was just sort of showing you that this Hamiltonian analysis allows you to kind of do some algorithm analysis. Okay, so here is the result. If you'll just look at the very top part of the page first. So again, the setup is this smoothness conditions, and our convergence rate is 1 over epsilon to the 7/4. So it's faster than epsilon squared. And so in fact, provably, this is the first result of its kind. Acceleration helps you to get past saddle points in non-convex problems. Moreover, there's Lipschitz constants, L to the 1/2 and rho to the 1/4 there. And they may look a little odd, but if you actually kind of put this side to side with the convex case, there the constants are Lipschitz divided by the strong convexity parameter alpha. That's called a condition number. And in fact, this L to the 1/2, rho to the 1/4 is effectively the appropriate condition number for this problem. So we don't have any free constants. It really is just a condition number. So in some sense, we've kind of solved the problem. Again, there's an O tilde there, so there's a dimension dependence being hidden, and that dimension dependence is again polylogarithmic. And it's for the same reasons before. We're using this coupling argument to get down to that thin slice of geometry. It turns out to be logarithm to the 6th here instead of the 4th, but again, I think that's an artifact. Okay. All right. Each section is going to get a little shorter now as we've kind of built up some of the appropriate structure. We're going to now start to put all this into connection with stochastics. So this is very recent work, last few months, and this is ongoing. So this area, I think, is going to be, at least in my own life for now, probably at least a decade, and I think a lot of other people as well, just beginning to emerge. So the basic scope is that everything you've heard about so far is differential equations and gradient deterministic algorithms with a little bit of stochasticity. But what about diffusions and Langevin? What about stochastic differential equations? Can they be asked to go faster? What's the optimal way to diffuse down a surface that's convex or not, or on a manifold? Okay, so these are things that have been worked on in bits and pieces in the past, but in this optimization framework, non-asymptotics, there's new questions. All right, so people have in fact asked this question: can you accelerate a diffusion? All right, so a diffusion, roughly speaking, is a bit of dynamics that adds in Brownian motion. Brownian motion is very noisy. And so there's been kind of an intuition that it's too noisy, that acceleration, if you try to accelerate, the acceleration will amplify that noise, and it will make you slow down. So there have actually been some theorems that are negative in this regard. Okay, but I don't believe those theorems because I don't think the scope is right. So they've been studying a particular diffusion, which is what's known as overdamped Langevin diffusion. You all know what that is, but I'll show that to you in a minute here. The work that we've just been talking about says that if we look at second-order dynamics, so maybe perhaps underdamped diffusions, those are the dynamics that give you acceleration phenomena. So what about in the diffusion world? Is that same kind of phenomena occurring for underdamped diffusions? Okay, so here's overdamped Langevin. So it's just a stochastic differential equation that has the gradient of a function. We're calling that now u instead of f, but it's the same. And we add to that Brownian motion. Okay, so the stationary distribution of this object, it'll converge to a distribution, p star, which is e to the ux, normalized. And you can discretize this numerically with Euler, and you get essentially a gradient descent algorithm, but where you add in Gaussian noise. Okay, so it's a little different from stochastic gradient. This is often called Langevin MCMC. All right, so there is some theory on this now. So this is very recent. There were asymptotic results and kind of spectral results, but those are limited. There's now some actual non-asymptotic results. So Dalalian in Paris has been leading some of this. He had a result showing that if you want to get convergence to the stationary distribution p star and total variation distance, you can get within an epsilon ball in number of steps, which goes as 1 over epsilon squared. Okay? And the dimension dependence is d in the numerator. Durmus and Moulin studied the same problem in convergence in 2 Wasserstein distance, which is a more friendly metric to be working with for this problem, and they got the same convergence rate with a simpler proof. Chung and Bartlett studied the same thing in KL divergence and got the same convergence rate. So is that the convergence rate for these stochastic diffusions? Can you do better than this? All right, so we studied instead underdamped Langevin diffusion. So now we have 2 equations. The Brownian motion is being added to the velocity, and then we're integrating the velocity to get the position. Okay? But it's still just a diffusion, and it has a stationary distribution, which is again proportional to e to the minus ux. There's a velocity term. You sample x and v, and then you ignore the v part to get the marginal. So this is a perfectly fine way to do MCMC. Okay, so we have now done the theory of this. We've done that for a discretization, which is again a simple Euler discretization. There it is. So there's Brownian motion being added to the second term. All right, and so here's the result, which is that the convergence rate is actually quite a bit faster. It's 1 over epsilon, not 1 over epsilon squared. And moreover, the dimension dependence goes from d to square root of d. Okay, so this is a more effective way to get to diffuse down the hill than classical overdamped Langevin, significantly better. Now, is that the best you can do? I don't know. So we don't have a lower bound currently. And there probably are some new tools, not new ones, probably old tools, potential theory or Malevin calculus are probably needed here to start to talk about this kind of the notion of an optimal diffusion. So that's ongoing work. And just a little bit of the intuition here. The intuition is almost really a simple numerical one. On the left, you have overdamped Langevin diffusion. You can see the Brownian motion having its effect. And on the right, we have our underdamped Langevin diffusion. And if you had to discretize those 2 curves with a numerical algorithm, you're going to want to discretize the one on the right. You're going to be able to make a much more stable discretization and move faster on the one on the right. So in some sense, that's almost a simpler intuition than the whole Nesterov argument. Okay, so I'm near finishing. Let me just give it, again, even shorter snippets now of some of the ongoing work. That work was for the convex case, and most of the MCMC work has been for the convex case. But now there's an emerging line of research on non-convex MCMC, and one way that's been very useful to analyze this is that we give ourselves a function to be that is strongly convex outside of a ball of size r. And within the ball, it's arbitrary, smooth but otherwise arbitrary. So there are lots of statistical problems where this is a very natural thing. For example, mixture models have this kind of structure, and you'd like to see how those two regimes interact in terms of convergence rates. So we've already started to do that for this particular problem. So here's a picture of strongly convex outside of a ball. You can see that for, there's convergence, the theorem is at the bottom. The convergence rate for overdamped MCMs in this setting is also, again, d over epsilon squared, and for the underdamped case, it's square root of d over epsilon. There also is a condition number kind of quantity there that involves the size of the ball and the Lipschitz constant appearing there, and we believe that particular constant. We believe that is, and again, a condition number. The proof idea here, if you're again a probabilist, you will like this. Instead of just doing a classical coupling, we're doing what's called a reflection coupling. We have a process X and we have a process Y, and they are reflections of each other. That allows us to reduce this problem to a one-dimensional problem along the line that connects these two things. That's critical to start to get these good dimension dependence in these class of problems. The one-dimensional problem just allows you to take the Ito lemma and apply it to the norm of the difference between X and Y, these reflecting couplings. That's a one-dimensional object, and just Ito calculus allows you to turn that into the underlying stochastic quantities, the Brownian motion and the drift. So Ito was really, really essential here to get this whole line of non-asymptotic results to go through. All right, I have 4 more minutes, and let me just now again briefly mention this is now into the dessert. So this was all about optimization and stochastics and diffusions. And again, there's just lots to do still here. If you're a young student in the audience, I hope your interest is piqued. There's more open problems than closed ones here. But we didn't really say anything about statistics yet. This was kind of probability meets differential equations meets optimization. So let's start to say at least something about statistics. Well, one of the core problems statistically is that if I take a functional, which is the population risk, what a statistician cares about, it is the loss function, the expectation of the loss over the population. You would like to characterize that risk, find its tails and find its optima and so on. But you don't have that risk because you can't take the expectation of the population. You're only able to take an empirical risk. Take a sample of people from the population and take the expectation over the delta functions. When you do that sampling process, your beautifully behaved population risk turns into a very ugly, at fine scale, empirical risk. So for a statistician, that's fine. That's just part of the 1 over square root of n things that we're used to dealing with. But for an optimization person, that's not fine at all. You're going to start an optimization algorithm on the right there, and you're going to run down and hit one of those little local optima and be stuck. Okay? So how do you get out of those local optima in a computationally efficient way? And so you don't just wave your hands and say simulated annealing or something. You have to be a real theoretician here and say how to do that. Okay. So we have been able to do this now. We've been able to characterize the amount of there's a quantity coming from empirical process theory which characterizes sort of how much noise is being added by the sampling process. And if that noise is not too big in terms of epsilon and the dimension, then we're able to actually find a second-order stationary point of the original function f, the smooth one, based on gradient descent on the rough function. Okay? So no new algorithmic tools are needed, just some new mathematical tools are needed. Here is the algorithm we're analyzing. I don't want to get into details again. It's the same kind of things with just a little bit of smoothing going on here. And this slide summarizes what we've been able to achieve with this, that kind of on the space of adding more and more noise, at some point you get to the case where it's information theoretically impossible to solve the problem. There's too much noise to do the inference. Below that, you arrive at a point where if you take an exponential number of queries, you can solve the problem. And we were able to reduce that all the way down to polynomial with this new framework. And then below a breakpoint, which is the one I wrote up earlier, e to the 1.5 over d, the new algorithm simplifies yet further just to stochastic gradient descent. We're now to prove that that's is inferentially correct up to that limit. And then there's another lower limit where stochastic Langevin is effective. Langevin's worse than stochastic gradient here, provably in this setting. Okay, so that was a little bit more for the experts in the room who are really kind of working on this or thinking about it. That's kind of where we are with statistics meets optimization. Okay, so let me stop. Let me pop all the way back to the top level. This field is not really a field, but it's a massive human undertaking to bring computation together with inference. And I think, at least in my lifetime, that's really been one of the biggest challenges around. And it's not just a challenge mathematically, it's a challenge almost sociologically. I'm both in a computer science department and a statistics department. And I will go to my statistics colleagues and I'll say, what do you know about computation? Isn't it highly relevant? You're doing algorithms and all that. And they will argue about whether R is better or Python is better. They just don't have a gut feeling of abstraction, modularity, and complexity in the same way. And that really is holding back the field. But I go to my computer science colleagues and I say, well, you have all these algorithms, like path algorithms and all that. But what about applying them to things that have stochasticity and are trying to do inference about real-world phenomena and get confidence intervals and do hypothesis tests? And they say, well, those problems, we don't really, those aren't our problems. They weren't given to us by CARP or whatever, okay? And that gap is really, really hurting, because if you go into industry, you see people trying to solve real-world problems at scale, needing good algorithms, but have inferential consequences, have error rates in the real world when these algorithms are being used. And those are now being uncontrolled because the right algorithms are not known for those class of problems. And so we're really in a world where we have an emerging engineering challenge: build systems that use data and computation and inference. Do it for the real world, for finance, for commerce, for transportation, and so on. And do it in a way such that error rates are being controlled. And we don't have the mathematics to support that effort. Right? So I think of this like about maybe in the 20s or 30s, where there was chemistry and physics, and people said, well, maybe we could build chemical factories, But a whole discipline called chemical engineering had to emerge. All right? And so I think a whole new discipline here, let's call it data engineering or whatever, needs to emerge that has mathematical challenges and underpinnings being faced and solved, like the chemical engineers continue to do, but that is really focused on this real-world class of problems. And so again, I think this is core to mathematics, is to take the emerging problems of the day, like Gauss did and others, and face them. And I think that these are those problems. Let me just say last word. I'm 40 seconds past. I wrote an op-ed called Artificial Intelligence, the Revolution Hasn't Happened Yet. I don't tend to advertise my own work too much, but that I would like to advertise. If you haven't seen that, please read it. There's a lot of buzzwords about AI and machine learning these days, and most of it is complete nonsense. And most of it is hype, and most of it is hurting progress of the field. They're not identifying this engineering set of challenges, and they're off on the grand aspiration of building a human inside of a computer. And I think that's neither necessary or sufficient for solving our real-world problems. So something like in the tone of the previous talk, quantum is interesting, exciting, but let's be careful about statements we're going to make. Same thing here. AI is interesting and exciting, but let's be super careful, because a lot of the things that are being said are just false. Thank you.
Thank you very much for a great talk. Professor Jordan will be available for questions from the audience during the intermission. Let's thank Professor Jordan once more.
Thank you.